Let me make
When's the
sure.
next exam?
Now the lecture is recorded. Okay, let's get started for today's lecture. First of all, let's talk about the exam. So we will have another exam, the unit exam next Tuesday, a week from now. And the coverage, I was checking the syllabus just now. We are still running a little bit late according to the schedule. So the coverage will not be the plan, but will be for chapter 4, 5, and 6, including this week's discussion for today's lecture and Thursday's lecture. So I'll email the class to remind you the exam on next Tuesday, and then I'll also update what would be the coverage. But before that, we shall be able to release the exam 1 grade, hopefully by this Friday. So this is the first thing I want to have a quick update, and the second is, of course, let's take a look at the material we are having. And to be honest, I'm still a little bit concerned about your reading and what is your learning plan for the lecture materials. As far as I can see, each lecture we introduce some new concepts, new quantities, and of course new equations. So it's better that you actually understand the material, not just be familiar with where I can find those equations, because equations usually they come together with conditions, and if you simply be familiar with the equations, then you don't know which equation to apply and what would be the modification for specific cases. So this is why I highly recommend that you read the textbook together with the slides, together with the examples. For both chapter examples and the examples I include in the slides. So that is the second thing I want to emphasize, and hopefully I will have your attention this time. So if we try to recall what we were talking about for last 2 lectures, we were talking about quite a lot of interesting stuff. So the first one was the second law of thermo. Now we are able to identify which energy input is better. The answer is work, simply because we cannot completely convert heat into work. So we have to waste some part of the heat when converting heat into work. And that wasted part, now we are able to express this by the entropy increase to the system. So over there, we had a mixture of second law of thermo and the third law of thermo. And when we think about the contents of those discussions, we have to be happy with the Carnot, reversible Carnot cycles, right? So there we need to understand we are going to have 4 units, and they work together to convert heat into work. And along the 4 units, we are having the isothermal processes, we are having the adiabatic processes. So we have to calculate those work and heat along each path. And then when we think about the efficiency for the 4 units, we have a general definition of the efficiency, which is the work over the heat input. And then if we are working with the reversible Carnot cycles, then we can further simplify that efficiency definition into Tc over Th, right? And then moving forward, we realize that if we complete the cycle, complete the 4 units, there's one quantity that will return to 0 after the completion. So this is the reason why we come up with the idea of a new state function, and that is the entropy. If we think about the entropy on this slide, we have this entropy definition. So make sure that you have the reversible process whenever you are going to design a process. And then this is a new state function of entropy. And then if you run the integration on both sides, then you are going to calculate the entropy change when you finish a cycle. So that is the reversible cycle. But how about the real cycle, irreversible? Then we are going to have a quite different heat related with that irreversible actual path, but the entropy change will be the same, simply because entropy is a state function, not depending on the exact path. And then in order to calculate not only the entropy change, but also the exact entropy at any moment, entropy of any moment, any temperature, then we need to have this third law of thermo. That will be the perfect crystal at 0 Kelvin. The entropy should be 0. Then we shall be able to calculate from the data S. It's not okay, it's 0 Kelvin. And then till the end of last lecture, we were also introducing some new energy equations. So instead of internal energy, instead of enthalpy, now we have the other two, which is the Helmholtz and Gibbs. So from the definition over here, then we try to take a look at the fourth derivative. I hope you are happy with the fourth derivative by simply looking at the definition of the four energies. We know du would be, and over there we know this would be TdS. So we derive those equations using reversible. But after the those discussions, we also understand that the four energy equations are state functions. So in reality, once we have those equations available to us, we can use those to any system. We're not confined by the reversible requirement. No. So there, if we are looking at this small amount of Q, that is TdS, and the work is negative PDV. Once we have this du for derivative, we move on and we derive all those other energy equations, right? So over here, there's one quick understanding. The internal energy could be expressed as a function of entropy and volume, right? And the enthalpy would be the function of S and P. This is from the mass that the dH, the fourth derivative, is expressed as a function of ds and dp. So this is why we know that the enthalpy itself is a complete equation defined by entropy and pressure. So A, Helmholtz energy shall be the equation of T, and V, the Gibbs energy shall be the equation of temperature and pressure. So there you can see that we are very happy. We are very happy with the last equation because we keep talking about, in reality, when we design the production, when we have the industrial lines, containers, reactors, we better not manipulate the volume, but stick with the temperature and pressure changes. So that is why if you look at the four energy equations for our daily life chemical engineering, the Gibbs energy will be the most convenient. And we will be talking about the Gibbs energy for almost all the remaining topics. So that's the reason. So now, if we try to take a look at that fourth derivative, I hope that mathematically you can recall that we could have the first order derivative, second order, and third order. And from math, there's one theorem, which is if you are looking at the high order derivatives, the order does not matter. If we have a function of f is fx, y, so the df over dx and dy should be exactly the same. When you switch the order, take the first derivative with respect to y and the second derivative with respect to x. So that two terms should be identical. So this is why Maxwell, he recognized this pattern out of the four energy equations, and he derived the so-called Maxwell relationships. So let's take a look at what was going on. So this slide was simply review the Maxwell equation. So mathematically, if we have this, then the fourth derivative could be expressed as we take the derivative with respect to x while keeping y fixed, and now we move on to take the derivative with respect to y while keeping x fixed. So this is how, if you have two parameters dominating the property, we can separate these two parameters and try to take a look at their effects. And of course, behind this, we have this still Gibbs phase rule, right? This is when the two parameters should be enough, or we have to express this as f is for some other cases we may have to use three parameters. Then this would be the fourth derivative with respect to each parameter. So anyway, move on. If we define that, for example, here we try to use Mary M as the partial derivative and N Nancy as the other partial derivative, then we have this very simple equation. So that was the fourth derivative we were talking about until now. Now, if we try to ask the question, if I'm going to take the the second order derivative, then what would be the case? So over here, if I try to keep both slides here, now you can see that this M Mary is with respect to x keeping y fixed. Now I'm going to take the turn to y. Now I'm going to take the second order derivative. I try to have this dm over dy. Here I'm keeping the x fixed. So this is the order. Firstly, we try to take the derivative with respect to x, then we take care of the y. And on the other side for n, we are going to take the first order derivative with respect to y, and then think about x, right? So mathematically, the two equations shall be identical. So they are identical, right? So this is what we have from math. Now, if you think about that equation, let's try to look at this equation. So the temperature is actually coming out of du, right, with respect to partial derivative with respect to s while keeping the volume fixed, right? So this is how we write down this equation. Du would be, no, let's try to move from here. U is a function of s and v, and we now know that the fourth derivative of u would be du over ds, keeping volume fixed, ds plus du over dv while keeping entropy fixed, dv. And we know this would be T. So that is exactly what I have over here. So now after that, you are going to take the second order derivative. So you are going to take the other order of derivative, which is, now we finished with this entropy term, but now we are looking at this volume term. So that would be the same as du over ds. Here, of course, we need to remind ourselves that the volume is fixed. Now, after this first order derivative, we are going to take another one, which is d this term over d volume. And of course, while you manipulate this, we shall keep the entropy fixed. So inside that the parentheses, we shall have temperature. So this is basically dt over dv, keeping entropy fixed, right? So this is exactly what I have over here. So this is when we look at the first item of the fourth derivative, we try to take a look at the d2u, ds, and dv. So that would be the first term, and on the other side, we are going to have this as d2u over dv and ds. And that is, if you try to follow the discussion, that would be together with a negative sign, that would be dp over ds over volume. So, so that is a simple application of the math we discussed on slide 5. So here you can see that we have some correlation between temperature, pressure, and the two variables. You may want to practice on your own side, but let's try to pick up, say, let's do this on the Gibbs Energy. Let's try to work together on this limited space. So we have this g as a function of t and p. So we know this dg would be partial derivative over g with respect t, keeping pressure fixed, dt, plus dg over dp, keeping temperature fixed, dp, right? And we have figured out that part is negative entropy, and this part is volume. Okay, then if we keep working on the second, we know that is dg, d2g, dt, dp should be d2g if you switch order dp and dt. So for the first one, this is basically the d over dg over dt p. Then we finish the derivative with respect to temperature. Then we switch to the pressure term, right? So this is the inside the parentheses, dg over dt, keeping pressure fixed, would be negative s. So this is why this is d minus s over dp. And of course, here you are going to keep the temperature fixed. On the other side, this I'm not going to repeat the writing running out of space. This is dv with respect to temperature while keeping the pressure fixed. So now if you try to look at the term we just wrote, this would be this term, this would be, so that is a term over here, and that is a term over there. All right. So try to practice, for example, looking at the entropy equation or the Helmholtz for derivative and try to figure out the corresponding Maxwell equation. Those are coming out of the second order derivative of those energy equations, and we have received another 4 equations. So it's a little bit messy on this slide. Let's think about why we are doing this. Now, if you look at the real life measurements, we keep talking about the PVT measurements. Those shall be straightforward in a way to us, but the entropy is not that easy. So we probably understand. We probably understand if we are going to carry out a process keeping the entropy as a fixed value. So here means entropy shall not change along that process. So we understand that if this is the reversible adiabatic, right? If this is a reversible adiabatic, then this is QREV would be 0. So there we can see that ds, which is defined as the QREV over T, then the entropy shall not change. So you can see that in order to measure the turnover dt over dv, keeping entropy fixed, it's actually not very straightforward. So this is why we hope to convert that into something else, okay? So there you can see that whenever we are going to have the entropy term, for example, the third one, this one, if you try to measure if the temperature is fixed, this is isothermal process. And along that isothermal process, we try to measure the entropy dependence on volume. And now if we are using the Maxwell equation, the equation 7 on this slide, we know this derivative is actually equal to PVT correlation. So this is why the Maxwell equation, those 4 equations are very useful for us to manipulate, to convert some really hard to measure quantities into PVT correlations. And I hope that after the first unit, we understand if we are going to solve for PVT correlations, we have multiple choices. Equation of states, variable, and those corresponding state principles. And at some point, you are going to use solver or some math softwares to figure out the numerical values. So this is the first part of today's discussion, the Maxwell equation. And I've added some notes on this slide, trying to further illustrate and convince you that the Maxwell equations are very useful if you are dealing with those quite hard measure quantities involving the entropy term, and now you are going to easily correlate that to the PVT term. So you can see that in a way we have those PVT and entropy. Those terms shall be the dependent and independent or fixed quantities in some measurements, and eventually we want to convert that always into PVT measurements. Okay, so that is the Maxwell equation. I think we have one example. I don't know whether I added that or not, but let's now try to move on the second concept. That is also a very interesting concept. So on the first slide, we realize that we should be able to, for example, the enthalpy is a function of S and P, right? If you are looking at the second equation, clearly that equation indicates the enthalpy is fully expressed by entropy and pressure. So the natural, or we call this as a pristine equation, would be H is a function of entropy and what is that? I forget. P. So again, here I want to show you the case that I cannot memorize those equations. And there is indeed no need to memorize those equations. But we have to be comfortable with the logical flow, how we are moving from one concept to the other. I think that really matters in thermal. So here we know that the enthalpy ideally would be expressed as a function correlating entropy and pressure. And now we know that the entropy is not very friendly to us. It's hard, and we have to design the reversible processes in order to calculate those entropy terms. So this is why we try to have the request. We put forward the request. What if I want to express entropy as a function of temperature and pressure. So what if we try to express entropy as a function of temperature, pressure, and then let's say, well, try to take a look at how we are going to express entropy itself as a function of temperature and pressure. We had some ds over dt or ds over dp term from the Maxwell equation, right? ds over dp, for example, over here, ds over dv over there. So that is also a quite interesting question. What is the exact expression if we try to write entropy as a function of temperature and pressure? And if we are able to achieve that goal, then moving forward, when we calculate the entropy and entropy contributions, then we could use these two equations. So let's move on to see how we can solve the two requests. First of all, we always start with the definition or the request itself. Here, if the request is we need to express entropy as a function of Tp, then let's move on and write down the full derivative of that equation. So this is the equation 9 here on the slide. dH is a partial derivative of dH over dt while keeping the pressure fixed. On the second term, that is dH over dP, keeping the temperature fixed, right? So we are able to move forward with one step to write down the full derivative. Then the full derivative will involve two new partial derivatives. So we need to take a look at this dH over dP. dH over dP. So if you somehow recall our previous discussions, whenever we have the fixed pressure processes, we are converting the heat flow into the entropy calculation. So that is indeed the definition of specific heat, Cp, right? So this term, dH over dt term, would be the specific heat of Cp. And the specific heat of Cp, by its own definition, it's always the heat needed in order to increase the substance by 1 degree C, or 1 Kelvin. So from there, we can also write down the Cp value as a genetic specific definition dq over dt. Of course, you still have to keep the pressure fixed. And there, if you connect this entropy term, if this is a reversible process, then this small amount of Q would be TdS, So this would be the small amount of reversible. So we added the reversible requirement to write down the equation. And then after that, we realized that Cp is also a state function. So there we don't need to bother ourselves again and again by the reversible. It's just along the process we need to formulate the philosophy, but after that this should be a general equation for any system, reversible or irreversible. Those would be all the cases we are able to use the equation for. So here we can say that using the Cp definition, using the reversible heat, using the entropy definition, we are able to write down the three equations in that equation 10. So at least for the time being, we are able to replace this partial derivative by T ds over dt, right? We are able to replace this term. Okay. Then how about the second term, dH over dP? What about the second term? We'd better also replace the partial derivative over dH. So now if we are looking at this term, dH over dP, let's try to see what would be the other useful equations for enthalpy. We don't have too many useful equations. We've used one, H is expressed as Cp. And the other is we'd better go back to its own definition. Or in a way, we need to go back and look at this full derivative coming out of the definition of enthalpy. So we know dH is TdS VdP. dH is TdS plus VdP. And here we need to have some term over dH over dP. Now I hope you can see what is going on. If we are going to divide on both sides by dP, then on the right hand side, no, on the left hand side, this is exactly dH over dP. So that would be T ds over dP plus V, right? So over here, we are able to also replace the second partial derivative by the term ds over dP. And the first term was replaced by ds over dt. So looking like now moving forward, we need to figure out ds over dt keeping pressure fixed or ds over dP keeping volume fixed. What would be that two terms? And I hope you realize that those two terms might be the Maxwell equation terms. So now if we try to look at this ds over dP, and what is the other term? ds over dt, ds over dP, ds over dP, ds over dt. Looks like we don't have that exact term, but let's see how we are going to manipulate that. So this is the general kind of flow so far. So we start, let me repeat the process. We start with the request. We write down the full derivative of that request. Now we move on to simplify to replace those new partial derivatives. So usually we have the available information. One is the definition of that quantity. Here is the quantity is enthalpy. And the other would be the full derivative and Maxwell equations, Cp, Cv definitions. So those would be the three resources we are going to use in order to simplify and replace those four partial derivatives. So let's try to follow the slides to see what was going on. So this is the full derivative of enthalpy, and we take we divide dP on both sides. So there, this is the left-hand side, the first term of the right-hand side, the second term of the right-hand side. We divide dP on both sides, and then we say the this term ds over dP. This is the exact term of the Maxwell equation of equation 8. Okay, so if this is the case, then we are going to express this dH over dP at fixed temperature would be negative T. We are going to replace this term. This is dV over dt pressure plus V. So we figure out this term. The other term, okay, the other term, yes, we have a better candidate. We could use this term to replace dH over dt. We could use a much easier term. Just go ahead and use Cp. right? Otherwise, we have to combine a few Maxwell relationships to really figure out what is ds over dt as pressure fixed. I think we are going to work on that in a minute. Okay, so we took a long way, maybe a painful way, but now we are having this equation. So H, when we try to express this as a temperature of pressure, we end up with this working equation, and it's quite convenient equation for us. Cp, if you come up with a substance, say ammonia or steam, we have those Cp values, especially Cp as a function of temperature. This would be the PVT, right? So now you can see that we are going to have those terms, and for any system, as long as we have the Cp value and a working equation of state, then we shall be able to evaluate the enthalpy change. I do want to take a look at this term, V minus T dV over dt P. Let's try to spend a minute trying to figure out for ideal gas. What is this term? If you have a piece of paper and a pen, let's try to take a minute to evaluate this term. Hello? Are we good?
Yes.
Yeah, thank you. So try to evaluate what would be this term for ideal gas. While waiting, let me check if the recording is working. Yeah, I think it's working. Okay. How do you plan to evaluate this term if I have a question like this for ideal gas? Well, nothing special. PV is RT is my ideal gas, right? PV is RT. Okay. So if I take the term dV over dt, keeping pressure fixed. So we need to evaluate this term. Then what would be the volume as a function of temperature? So over here, this is a d. What is the volume? The volume is RT over P dt. And here we keep pressure fixed, right? So if pressure is fixed, R is a constant, then this is R over T, R over P dt over dt at fixed pressure, right? This is basically, I'm going to put it over here. This is basically R over P, right? R over P. So if this is the case, then I'm going to put it over here. This would be V minus T times what? T times R over P, right? So here I have TR over P, which is V minus V, which would be 0. Okay, I think almost here you've started the idea that thermal is a little bit of math, a little bit of concept, a little bit of converting one term into the other, and that is indeed required by the understanding and the learning of thermal. So why I want to point this out? So if you recall in the past, we only have this term. And I can recall that on a previous slide, we said that enthalpy will be depending only on temperature for ideal gases. So that is actually the proof using the equation here on slide, on the equation 12, why enthalpy is only depending on temperature for ideal gases. That is because the second term, this term will be 0 for any ideal gases. So this is why we are going to get rid of the temperature dependence for ideal gas for the enthalpy calculation. And we will use the idea to understand the following residual property calculation. So this is what I want to warn you what is actually coming. Okay. So how about the second request? The second request is we try to put entropy as a function of temperature and pressure. So I'm not going to write down too many stuff. I'm going to just read the slides and try to walk through those equations together with you. So we take the full derivative. ds is a partial derivative with respect to temperature, keeping pressure fixed, dt, plus the second term, ds over dp, keeping temperature fixed, dp. And then the useful stuff is, well, we know what would be the ds over dt. That is because Cp would be T ds over dt. Right. So this is the slide we have on the equation. So Cp is T ds over dt, keeping pressure fixed. So there we just manipulate, we divide T on both sides of the equation 10, then we have ds over dt. So this term was from the definition of the specific heat. Then we need to look at the second term, this partial derivative. This ds over dp, then we are able to find the corresponding Maxwell correlation. So there very easily we are going to use this equation to quickly figure out, I can rewrite the equation 13 into the equation of 16. Okay. And over here, you can see that for any entropy change calculation, as long as I have the Cp value, as long as I have the PVT correlation over here, or some type of equation of state, then I should be able to evaluate this equation 16. Are we good so far?
Yeah.
Okay. So you definitely want to read the slides and try to write on piece of paper to see if you are happy with those notations. The full derivative, partial derivative, replacing one term by the other. Please do the homework if you have not reviewed the slides before the lecture. You definitely want to review those slides after this lecture.
Will you post this slide with the notes as well?
Yes, for the past few lectures, after each lecture, I always post the slides with notes. So
Okay.
if you go to Canvas, you should have 2 copies of the notes. One is the clean version. The other is my massive version of the slides. Okay.
All right.
Yeah. So moving forward, once we receive this equation 16, and you probably vaguely recall the alpha and beta coefficients we were talking about in the lecture of equation of states. Then equation 7 and 18 are not new equations, but simply we try to take advantage of this compressibility or expansion coefficient. So sometimes with some textbook, you may find equation 17 and 18. Those equations, they may appear a little bit strange or a little bit complicated, but I hope with those slides now you can understand where those equations are coming from. I think I keep emphasizing this is very critical to the learning of thermal. So now if we put together that equation, and we are going to discuss the last part of today's lecture, which is we start with some random request. And of course, now we see the request has a practical reason, because we want to express H as a function of temperature and pressure. We are really good at the PVT manipulation and measurement, and so does entropy. S is temperature and pressure. And now we are able to write down the full derivative, and we move on using some equations to derive the Maxwell related calculation equation. We just finished talking about those. So here, again, I want to remind you, we are using those CP definition. We are using the other definition of entropy definition. We are also using the Maxwell. Then with that three resources, we shall be able to derive. We shall be able to derive the two equations here. And you realize this is useful to calculate the delta H, right? If we take the integration on both sides from state 1 to state 2, from state 1 to state 2, then we figure out the change of enthalpy and entropy. But sometimes we are interested in the exact value, especially when you are trying to decide what should be the strain of the inlet and what would be the outlet flow of the process. So this is why the exact value is also quite important. And the exact value is nothing special. It's just delta H would be H minus H initial, right? Delta S would be the S of interest minus S initial. So here is the concept or the understanding. Whenever you are going to pick up the initial, you try to take advantage of the reference. So that is indeed the reference condition. And we hope that the reference, at the reference condition, we have lots of data. We have the table, we have appendix, we have the measurements available to use. So far, we've talked about this type of reference states. I hope you now recall the standard state. And I also hope you recall the troubles we had in chapter 4. There we have this special temperature. It's not really special. It's simply because we have lots of measurements at this 298 Kelvin. So in reality, when we try to calculate those exact values, we try to think of the standard states if we can take any advantage of that standard state. And we also think of that room temperature, 25 degrees C. We have lots of measurements. Are we able to refer to that as the initial reference? So that is the philosophy in real life problem solving. So the last slide, we will come back after today's lecture. I hope you will be able to understand why now we can move forward and we try to put together some new quantity, S of R, H of R, the so-called residual property. So now let's move on to see what we are going to talk about, or how do we come up with the ideas for those residual properties. So here is one slide to remind you about standard state. So before moving forward, if we are having some initial, some final for the delta H, delta S as a function of temperature and pressure, I hope now we can answer that. I have the working equation, right? But if the question is, I want to calculate the exact value, what would be the useful initial reference? That is very critical. So for the initial reference, we hope that if the quantity of interest, if their initial values would be 0, then this is super great. So the difference should be exactly the value of interest, right? So now let's try to see whether we can achieve that. But before that, let's try to recall standard states. In the previous slide, we had that discussion. For standard state, we need to separate the liquid and gases. For liquid and solid, even solid or gas, we define this pressure would be 1 bar, right? Or this is 100 kPa, and that is from IUPAC recommendation of the standard state definition. So at this low pressure, so for gas, if this is 1 bar, we can treat this gas very comfortably as ideal gas. For liquid and solid, we have the 1 bar requirement, and we have this as a pure liquid or solid. But we don't have the other assumption to go with it. This is the standard state. So you can see that temperature was never discussed in the definition of standard state. Yet, in reality, we have our own practical standard state. This is because the temperature at this 25 degrees C is so convenient to us that we've done lots of measurements to understand the gas phases. So this is why when we talk about gas, by IUPAC definition, purely 1 bar ideal gas. And our human being, us, we added another term. This is 1 bar to 900.15 Kelvin ideal gas. We're not trying to overwrite the IUPAC definition, but we just make this more convenient for the actual calculation. Okay, so this is the standard state. So now if I put together this slide, I hope you are not surprising at all. So there is nothing special. We still have the hope that we are going to move from the initial state, and now we try to take advantage of the standard state. That is the ideal gas, and that is the final real gas. And that would be the question we are hoping to answer. What would be the exact enthalpy at this temperature and pressure condition? So using the previous slides, we are able to calculate this delta H, right? Moving from the initial to the final. On the other side, this is a state function of enthalpy. If we are going to design our own process, I can also express this as this is delta H1, delta H2. For the calculation itself, this is delta H is delta H1 plus delta H2. And of course, the delta H itself is H minus H naught. And we will check if this is possible for the ideal gas. Okay. For the delta H itself, also, as we saw from the previous slides, we are using, this is delta H. So we are moving from T naught, P naught to TP. And this delta H, we are able to evaluate using the equation we just derived, right? So far, nothing special. We just check those concepts using the standard state, then further located at this ideal gas state, and we try to write down the delta H change as the two different combinations. Now, if you try to take a further look at the first pass, we are moving the initial ideal gas from T naught, P naught to a higher temperature, but keeping the pressure at P naught. So if this is still a low pressure, then the ideal gas assumption is a valid assumption here for this pass. And then the second pass, when we are moving from P naught to TP, this is the isothermal process, right? Keeping temperature fixed, changing the pressure, while the previous was the isobaric process, keeping pressure fixed, changing the temperature. So that is, I hope the design, the past design is also quite obvious to us. We can change one parameter, keeping the other fixed, and so on. So still, we have not figured anything special over the design. I probably have to skip the example problem. It's nothing special. I should have this example problem at some earlier slide. So I'm going to skip that and leave this for your reading. So now if we think about or put together the general path here. So let's try to recall what we have. This is the initial, this is the final, this is TP, this is ideal gas, T naught, P naught. We are moving to this as a T, P naught, and we are moving to TP. So on this slide, we are actually adding the term. We are adding this term. We call this as the imaginary TP condition. Okay. And that will behave as ideal gas. So let's try to see. So here still, this is the initial. T naught, P naught ideal gas. This is our reference state. Firstly, we keep the pressure fixed, move this to the temperature of interest. So this is the final temperature of interest. And then secondly, we are moving to not directly to the final, but we move this to the temperature of interest, pressure of interest, but we assume it's still ideal gas. So this is exactly what we have. We move this to T and P naught, and now we move this to T and P. Not exactly at the final, but we try to assume this is behaving like ideal gas. And then lastly, of course, we need to move from the imaginary ideal gas behavior at TP to the real gas at TP. So we try to carefully evaluate when we are moving the temperature and pressure, the state of the gas is changing from ideal to real. So here we try to add this imaginary condition. saying the temperature and pressure are at the exact real temperature and pressure, but we try to assume the behavior of the gas is still ideal gas. Then what would be the difference between the assumption? And here we define this as the residual property. So you can see that the residual property is a measurement of ideal gas, real gas, their difference. If the residual property is very small, then we can see that at this realistic TP, the real gas still behaves like ideal gas. If the residual property is quite significant, then we know that there's a quite deviation from ideal gas to the real gas. So that is another type of measurement to see the gas state. What is the deviation from the ideal to the real? Okay, so this is the first introduction of the residual property. We'll see in a minute on another slide about that concept. So now if we try to put down all those equations, we have those initial, those are not changes, that is a change. So we can see that now for example, delta H will be the difference between the H of interest minus H naught, right? This is ideal gas at T naught, P naught. Okay, so that would be same as delta H. Here I was using P naught, so this is the first pass. We try to move the ideal gas to a higher temperature, but still ideal gas. And we try to move this to delta HT. Now we try to move the ideal gas to high pressure, but we still assume this is ideal gas. And now eventually I'm going to move the imaginary ideal gas behavior at TP to the real gas behavior. And that's the difference. We call this as HR.
Are there residual properties in the appendix?
We'll talk about that in a few minutes. So here we are having the equation from the design of the path. So we have those quantities, right? Or if you look at this equation, so H of the final shall be connected by the three different passes. That is the initial true ideal gas at T naught, P naught. That is also the ideal gas at T, P naught. This is T naught, P naught. This is at T, P naught. This is at T, P, but we still assume the ideal gas behavior. This is the difference we are going to add. So that's the entropy equation. Okay. Then you can see that if we follow the previous discussion, we are able to calculate this part. We are able to calculate this overall part. And we are also able to calculate that part. Now, if we add some other condition into this, we shall be able to measure what would be the difference between the real and the ideal gas at the same temperature and pressure. Or in a way, we are able to measure the new defined residual property. So this is a little bit confusing. This is a new request we put forward in today's lecture. The previous tool would be we try to express enthalpy and entropy as a function of TP. Now we try to understand if I'm going to assume the gas at the high temperature, high pressure, if we assume this is still the ideal gas, what would be the deviation from the real measurement. And that deviation, we call this as a residual property. So now let's officially define this residual property. So we say in thermal, the residual property is defined as a difference. The residual property itself is the difference. So HR is the difference between a real fluid property and the ideal gas property, both considered at the same pressure, temperature, and composition. So it's just out of our imagination that I know this is real. There's no problem at all, but I just want to evaluate what would be the deviation or when I cannot safely assume ideal gas behavior. So in order to quickly evaluate whether or not we can assume ideal gas behavior, then we need to evaluate this residual property. So if we look at the definition of residual property, M is any value of interest to us, then the residual property at this temperature and pressure is defined as the actual value of the quantity, whether it's entropy, it's enthalpy, it's volume, or any state value of interest, then we can measure. And over here, we try to have the assumption of ideal gas behavior at this temperature and pressure. I'm having some trouble with my internet because the iPad does not show the update. Still not showing my notes. Uh-oh. Okay. So that is the definition of the residual property. Are we happy so far?
Yeah.
Cool.
Yeah, thank you.
Yep. So now let's try to take a look at how do we actually calculate this residual property. I think my iPad is not working. Let me switch to the. It's going very slow. Let me switch to the other share. So on this slide, I hope that we officially introduce the residual property. Now moving forward, let's try to evaluate some residual property. So on this slide 22, I was just writing down for example, the residual property of volume. Then according to the definition, it's V of R, Tp, this is the real temperature, the real volume, this is still assumed ideal gas behavior. So for the volume calculation, it's quite easy that we can take advantage of PV is RT. So at this temperature and pressure, RT over P shall be the ideal gas behavior value, right? So what about, for example, the Gibbs Energy, the enthalpy, those residual properties? Now let's try to take a look at the residual property calculation. So we kind of repeat the previous steps. If we want to calculate the residual property at this temperature and pressure, we need to recall the definition of the residual property function, which is M of R is N minus M star. So the star is to remind us that at this star condition, we are assuming ideal gas behavior. Okay. So now if we try to take a look at this residual property, we try to take a look at the fixed temperature process, for example, then we using this this definition, we take a partial derivative on both sides. So over there we have this partial derivative over dP, keeping temperature fixed, dm over dP at the same temperature, and this ideal gas behavior dP at that fixed temperature. Okay. So now if we are moving, because we are looking at the pressure dependence, now if we are moving from P naught to P, then on both sides, we just evaluate what would be their value. So here on this slide, I put this data. It's annoying, I cannot write. Let me try to figure out how I can write on this. No, that will take forever. So this is data M. Oh. And then if you try to express this data MR, then this would be the two term, and the remaining term would be simply the integration for these two terms. Okay. I have this highlight term. I mean to leave this to you to read and figure it out. So that is a question for the class. So I was saying that when P naught goes to 0, then at that P naught condition, the HR, SR would be 0, but VR is not 0. Okay. So I don't have the explanation here on this slide or in this lecture, but I hope when you are reading the slides of the lecture, try to answer this question: why when P naught goes 0, I'm going to have those equations. That term would be 0, that term would be 0, but this is non-zero, and you should be able to write down the evaluation of the VR at this 0 pressure. So if we try to take a look at VR, we just described this is just a V minus this is ideal. And then we simply have V PV over R. How about that V? That V, we are able to figure that out using equation of state or using other correlations with the help of appendix, right? If we know the TP value. Now let's move on. Let's try to finish the discussion of HR. So the HR is H minus the ideal gas condition of the enthalpy. So if we try to take a look at the fixed temperature process, then like the previous slide had, we are going to have this dH over dP. We try to take a partial derivative with respect to pressure on both sides. Then this is a dP keeping temperature fixed throughout the equation. So here we are going to have dH over dP over T and dH star over dP over T. And I have this quick evaluation, that term would be 0. So that is exactly what I wrote on the slide for the ideal gas. The ideal gas enthalpy does not depend on pressure. So this term would be 0 for any ideal gas. So this is the check you have to make. This is the question. You have to check why I can quickly evaluate this at ideal gas. This is 0. Now the enthalpy, no, the residual property as a function of pressure would be simply dH over dP at fixed temperature, right? So what is dH over dP? As I have over here, this is the general term over dH. So if I try to manipulate and have the dH over dP term keeping temperature fixed, so you can see that I'm going to divide on both sides by dP and keep temperature fixed. So if temperature is fixed, then this term goes to 0. That term goes away. Then dH over dP at a fixed temperature condition would be simply V minus T times dV over dt. So that is the term. Okay. So now in order to evaluate this residual property, we just take the integration on both sides from P naught to P. And we have the equation to evaluate what would be the HR. And of course, we need to figure out, like I have on previous slide, what was my initial HR at this zero pressure. So I have two questions for you for this class, and we will come back next lecture to check if we are good on the understanding. And that is actually the third concept I did not explain, but I hope you see there's no special reason why we pick up fixed temperature to evaluate. In order to evaluate the HR, I can pick up the fixed temperature process or fixed pressure process. Here, we figure out that the fixed temperature process is very convenient to get rid of a few terms in our equation. So this is why in order to evaluate HR, I designed this fixed temperature process to calculate the residual property. So that is the other note. Otherwise, you may wonder why all of a sudden, once you have the HR equation, why you try to pick up the fixed temperature. Is that any kind of assumption over there? No, that's just our choice of method. Okay, I think I have to stop here, but try to think about the two questions I leave to you. One is on the slide 23. At this zero pressure, this residual property will be 0 for HR and SR, but not for the volume residual property. And the other question is try to revisit how we can prove this term will be 0 at ideal gas. Okay, so that's all for today. And I left you with one example question. How do we evaluate the residual properties using the steam table again? Okay, we'll have a quick revisit on the two questions and this example problem this Thursday.
Okay, thanks, Dr. Huang.
Yep. So please read the slides. This is a little bit heavy of new concepts and then some manipulation, the design of paths. So it's getting more and more interesting or more and more complicated when you think about all the materials we have covered.
Professor?